Okay, let's do some more carbonyl chemistry. So now we're going to move into carboxylic acids instead of and away from aldehydes and ketones. We have a general sense of how carbonyl compounds react, right? Nucleophiles add to the carbonyl carbon. We break the carbon-oxygen pi bond. We make a lone pair on the oxygen. When we move into carboxylic acids and their derivatives, what we find is that that's not the end of the process. And the good news is that this doesn't get that much more complicated. The bad news is that there's about 1 million different versions of this reaction, and so we're going to have to really have a system to kind of keep track of what can happen and what does happen and all that other kind of stuff. So without further ado, let's get to that system. All right. The first thing I want to talk about is when we have a carboxylic acid, and we add an alcohol. Right? So I think without really even knowing where this is going necessarily, we have a pretty good sense of what can happen. So I'm just going to use ethanol. Again, we can substitute any alcohol, and I'm going to throw a little bit of H plus in here as well, just to kind of get things going. Right? So without knowing anything else, we look at this and we say, all right, we got H plus in there, we have a carbonyl. The first thing we're going to do is we're going to add H plus to that carbonyl and make the carbocation, right? This is pretty standard carbonyl chemistry. No surprises here. Now, once we've got this, we've got a carbocation at this carbon. We have a poor nucleophile, but when you've got a carbocation, poor nucleophiles will work just fine. So once again, the nucleophile is going to add to the carbonyl. We're going to break the carbon-oxygen pi bond. We're going to make a lone pair on the oxygen. This is basically the same thing that we did when we made hemiacetals and acetals before, right? All of this looks very familiar. But the only difference is that we have another OH group on here. So when I draw this next intermediate, pay attention to what's attached to the carbon, right? When we did hemiacetals and acetals, we had 2 oxygen groups attached to the carbon. We talked about kind of what to do at that point. Now we're going to make it just a tiny bit more complicated because we're going to have 3. All right, so once I've added that there, now I've got this R group somewhere. We got our carbonyl carbon, we got an OH here, we've got an OH here, and we've got this ethanol group that's added on there. Right? And so notice that now we have 3 oxygen groups. We have oxygen group, and then the ethanol. And so the question is, what can happen here, right? We have a couple of things that can happen. We can neutralize this. We can lose H plus, and we'd be left with this kind of. Yeah, I need to erase these because this looks like other stuff. We can neutralize this and lose H plus, and we're left with this thing that kind of looks like a hemiacetal but has an extra oxygen on it. That's not going to be terribly stable. It's not really going to. Stick around for very long, because if we just neutralize this, what's going to happen is we're going to add H plus somewhere else, and then we're going to be off and running again. And so instead, I'm going to kind of combine those 2 steps. So we're going to lose H plus from here, and we're going to add H plus somewhere else. Right? And this is one of those steps where we kind of wave our hands and say, oh yeah, the H plus goes away and comes back, and it goes here. Right? And we're going to put it on one of the OH groups. And you might ask, well, why that particular position? And the answer is, well, it's not that particular position, right? There's a bunch of different places that this H plus could go. It could come back and add on here, but of course, then you're just back where you started. So it's more interesting for us if we add the H plus to one of those OH groups. That is what we're going to do. Now, it doesn't matter which OH you add it to, because they're both they're both equivalent to oxygens, right? So once we do that, of course, now you'll notice that we have a good leaving group here. And so we have a choice. We can lose H plus from here again and neutralize and come back, go backwards through this pathway. But what's more interesting is if we lose H2O, right? We can lose H2O. We can use the lone pair on that oxygen to stabilize the resulting carbocation, and what we get is we get another one of these positively charged oxygens. Now, of course, this is, once again, we have a choice to make, right? We can have other things come attack this position, which may or may not happen, or we can just neutralize it, minus H plus, and make ourselves an ester. Now, esters are very stable, right? So this is very stable. And so it's going to be hard for this to react, right? We can add H plus to it, but this compound, if we have this attacked by something, whether it's water or ethanol or anything else, what's more likely is whatever just attacked it is going to leave again as a leaving group. We're going to end up back at this ester. And so what we know just from our standard carbonyl reactivity is if we take a carboxylic acid plus an alcohol with H plus around, we're going to add H plus to that carbonyl, we're going to have our alcohol attack. We're going to do a little bit of maneuvering to make a good leaving group, right? We're going to move the H plus from the ethanol to one of these OH groups, and then we're going to lose that leaving group. We're going to lose water and make this positively charged ester compound, which then we can just neutralize by losing H plus and make an ester. So carboxylic acid plus alcohol gives us an ester. Right. So that's the first mechanism in this chapter. We're into chapter 18 now, carboxylic acid derivatives. And what this one does is it uses a lot of the same steps that we saw in the hemiacetal and acetal chapter, with the added twist of we make a leaving group and we remake our carbonyl, right? We have a carbonyl in our starting material, the carboxylic acid, and we have a carbonyl in our product, the ester. And so when we have carboxylic acids, right, we're going to have a carbonyl in the starting material and a carbonyl in the product. So that's going to be different from chapter 16, where everything started as a carbonyl and then ended up as things like acetals or aminals or alcohols or those kinds of things where the carbon-oxygen double bond was broken and never kind of restored. So that's going to be the theme for this chapter. We're going to see a whole bunch of these in the next couple videos.